Wait, can we turn it in right now?
I will give, just in case, hold on, don't give them to, well,
No?
I will give some help, something, so you may want to hold them until I have spoken the first 5 minutes, just to make sure. Let me put it this way. If you got the answer of the units in the last part, the same as you got by hand, turn it in. If not, I'm giving you some help.
Wait, I thought it was supposed to be off note a little bit.
The entropy generation, you got the entropy generation in 1 hour, the same as you got in the by hand calculation, we're okay. If not, you may want to work some more.
Wait, the entropy should
All
be.
right, I have a lot of material to cover, so I will give right now a little bit of help with the homework so I can start on the real material. Something that I saw that was not necessarily clear to all of you is the difference between the homework problem where first we mix, if we have initial state, one mass at temperature 1, another mass at temperature 2, we mix them adiabatically. What is the final temperature and what is the entropy generated by the process? Versus the unison problem, which is a continuous time problem. The units are different. And as a matter of fact, different terms of the entropy balance are active. In the case where I have initial state mass 1 at T1 and mass 2 at T2, final state mass M1 plus M2 obviously at T final. What is the entropy balance? The entropy balance is the left part of the term, which is the SPT, will give us that S at the final state, which is going to be M1 plus M2, S at the final state, minus S at the initial state, which is the sum of the S's from M1 and from M2, so minus M1, S hat 1, minus M2, or let's put parentheses, plus M2, S hat 2, is equal to what? In that process, there is no flow in or out in my combined system of the two masses. So the integral, the sum of k equals 1 to k of m dot k s hat k, integral of that from state 1 to state 2 dt is 0. There is no adiabatically, so the integral of q dot over d dt from state 1 to state 2 is 0. And the last term is the integral of s dot gen dt from state 1 to state 2. And what's that? That's the total entropy generated. So that's the S gen. So in that mixing problem, you would get S gen equals mf S hat f minus m1 S hat 1 minus m2 S hat. Okay? And you need to calculate the S hats. So with the proper integral using the CP expression you have found, and careful, you integrate from a reference state. So each of those S's Si is going to be, all of this, by the way, was at the reference pressure. And we found out what is the reference temperature, right? So Si is going to be as reference, which is at reference at 25 degrees C, 1 bar, plus integral, because in the process everything is at 1 bar. So everything is at standard conditions, before and after, 1 bar. Okay, 1 bar, 1 bar. Standard pressure, not standard condition, standard pressure. Okay, so pressure doesn't change, so the integral of S is going to be Cp hat. I'm not going to write for you, but whatever. dt. Careful, it has to be from T reference to T. You can't take T reference 0. And careful, it has to be not degrees centigrade, but Kelvin. What do we do in unison? We don't have the same problem. Unison, we can only deal with continuous streams. What is the analogous continuous problem? It is where you have, now, not M1, but a rate, M1 dot, at the temperature T1, feeding with another mass at the temperature T2, adiabatically, and we have flow M dot F, TF. Units now are per time. Careful. Okay? Here, it's actual M1, 1 kilogram, 2 kilograms. Here would be 1 kilogram per hour, 2 kilograms per hour. Clear, everyone? Question, anyone? All right. Now, what's the balance? It's going to be different terms that work out, that are not zero. It's not those terms. The left-hand side is going to be 0. What gave us this was the integration of, of the ds. But the balance is ds dt. What's that? That's 0. Steady state. So that's 0. And now you have the, I'm not integrating this in the differential form, so that's going to be the sum of m dot k s hat k. That was 0 before. That's not 0 now. This is my system. I have 3 flows, in or out. K is 3 here. K equals 1, 2, 3. Here the in and out was 0. Plus Q dot over D, which is adiabatic, so that's 0, plus S dot gen. Here the unit of S generation is kilojoules per Kelvin. Here would be kilojoules per Kelvin per time, per hour. Clear, everyone? So what's the resulting equation? The resulting equation, what's the convention for m dot k's? If they come in positive, if they leave negative. So in our case, where we have the two stream mixing, this would be m dot 1 s hat 1 plus m dot 2 s hat 2 minus m dot 1 plus m dot 2, which is the same as m dot final. Let's see what, okay, so minus m dot final. We're out. Times s hat final equals plus s dot gen equals 0. And then you get, not s gen, s dot gen equals, move everything to the other side, and you have mf s dot f, sorry, m dot f s dot f minus m dot 1 s1 minus m dot 2 s2, which is exactly the same S's that I have here. These are exactly the same quantities. Here, though, would be, let's say, 1 kilogram, 2 kilograms, 3 kilograms. Here is 3 kilograms per hour, 1 kilogram per hour, 2 kilograms per hour. So numerically, the two will be equal if we're talking about duration 1 hour, which is what the problem is. Yes? It's the same thing, because that's change.
Okay.
So if it's paired like that, Celsius or centigrade is the same. But when you calculate here, that integral, very important. If the result is anything than a linear expression, the 273.15 doesn't cancel out. Look, you'll never go wrong if you use Kelvin.
Why do you switch it to Kelvin? I couldn't figure that out.
What?
The mass entropy. When I did it on Unison, I couldn't figure it out. So I had to dip everything.
No, you said it's the same. You don't need to worry about it.
Oh, so what's the conversion then?
Well, the change.
If you're talking about entropy per Kelvin, is the same as centigrade.
Well, how do I know that I did it right? I did it 2 different ways.
I don't know, but what I'm telling you is you can see now why the answer should be the same. That's all they have. That's all they have I wanted to give you.
But wait, how do I change the units though?
You don't. It's on the same scales. It's literally equal to the same.
Entropy per Kelvin is the same as entropy per centigrade.
So we're talking about you.
I know, but I just want to change it to
You
Kelvin.
can't.
So what? I turn it in?
Yes.
If you found the same answer for the unison problem and the calculation by hand of the analogous problem, turn it in. If not, turn it in Tuesday, or if you haven't worked on it yet. However, the other side is, we don't have much time before the exam. I need to assign some more homework before the exam. I will assign a new homework assignment today that will be due. Obviously, we don't have a class on Monday, so it will be due Monday next week. So, all right. So I will assign, I'll post a new homework today, and that will be due Monday, 10 days from today. Okay? And I may even assign another homework that will be due Wednesday. When's our exam? No, we still have. So I'll assign that. And that will be, if not entirely, largely from the test. All right. Today I'm going to do a very important derivation, and as I mentioned last time, this is done in your book correctly, nicely as a matter of fact, but in a very confusing way because it's trying to derive at the same time enthalpy and entropy, so it's taking one step one, another step the other, then back to one, then back to the other, and doesn't explain certain concepts clearly. But, so, I guess let me quickly do one more equation before I go to the main objective of today. So we have derived previously that, okay, so CP and CV calculation from volumetric equation of state. EOS stands for equation of state, and Cp star of T or Cp star of T. Of course, if you know Cp star, you know Cv star and vice versa. The difference is just R. So we have derived last time that the partial of Cp with respect to pressure at constant temperature is minus T second partial of molar volume with respect to temperature at constant P, which is equation 6.237. So that means that I can integrate, if I keep the temperature the same, that's Cp at pressure P2, temperature T, minus Cp at pressure P1, temperature T. So since I'm talking about constant temperature, dCp is simply this times dP. So that's going to be equal to the integral of minus T partial V, second partial V, with respect to T at constant T, dP, P1 to P2. But because the temperature is constant, this is dP at a constant temperature. We're doing this at constant temperature. I can pull it out, and let me put comma T here to make it clear. Constant temperature, I'll put comma T. Okay? I can pull the minus T out. Now let's choose P1 to be 0. Okay? Let's then I get Cp at P2 comma T. What happens to Cp of P1 comma T if P1 goes to 0? Zero?
Depends.
No.
We don't know.
Yes. Exactly. Cp star of T. As the limit of P1 goes to 0, we definitely are ideal gas. Any fluid in the limit pressure goes to 0 becomes ideal gas. So that becomes Cp star of T. So that becomes minus Cp star of T equals minus T integral 0T P2 T of second partial V molar with respect to T. So we have the expression 6,410. That's, oh, now let's rename P2 to P, to any pressure P. That means that I can write that Cp at any pressure and any temperature, moving this to the other side, equals Cp star at any temperature. Remember, Cp star only depends, of course, on temperature, minus T times integral from 0 T to P, P2 has been renamed to P, second partial of molar volume with respect to temperature over P dP. Although, as we'll discuss later, this is not always the most convenient form, because the typical equation, volumetric equations of state that we have, give P as an explicit function of V molar and temperature, not V molar as a function. So you would have to work further with it or rewrite in a different expression. But I will stop here at this point, which is equation 6,410 in your book. And if you work in the same way with Cv star, you get in a similar fashion from 6,236. I'm not even going to write